We present a novel, silhouette-aware image warp for high-quality free viewpoint image-based rendering of complex scenes. Existing approaches depend on accurate 3D reconstruction. Urban scenes have complex objects and depth discontinuities, such as trees and cars, which are hard to reconstruct, resulting in rendering artifacts shown on the left. As shown, our silhouette-aware approach greatly reduces the artifacts. We start with 10 to 12 input images and use computer vision algorithms to calibrate cameras and create a dense point set. Our approach has three main steps: user-assisted point processing, silhouette-aware warp, and final rendering. We start by a user-assisted point processing step. The user first marks important silhouettes, which help our algorithm handle occlusions correctly. Typically, this takes less than 1 minute per image. Multi-view stereo gives more than 100,000 reconstructed points in each input view. Our approach decimates the point set while retaining a uniform spatial distribution of points. Fully reconstructed regions or holes are filled in with new points using depth from existing neighboring points. These points do not augment the reconstruction, they merely provide constraints for stabilizing our image warp. Points with incorrect depths, for example on glass windows, can be manually removed after the decimation if needed. Please refer to the paper and additional material for more details. The sparse point set and the silhouettes are used to define our new warp. We create a warp mesh for each input image. We add special elastic triangles around silhouettes. Without silhouette constraints, depth continuities cause severe distortion, shown here. Our silhouette-aware warp preserves the outline of foreground objects even for wide baseline warping. The elastic triangles shown in red represent disoccluded pixels filled in from other images during rendering. Our rendering pipeline first selects 4 images to warp. Blending weights for the warped images are computed using the view ray angle for each pixel. The elastic regions for each image are given very low weights since they are heavily deformed. The warped images are blended to give the final image. We use Poisson synthesis as a post-process to alleviate the spatial. We now show our results. The tree dataset is a challenging example that contains poorly reconstructed vegetation. Our approach generates reasonable novel views. The Castle dataset is a standard multi-view stereo dataset. We also compared to the piecewise planar stereo method for this dataset. In this paper, we present a novel approach for perceptual audio rendering of complex virtual environments containing hundreds of sound sources. Real-time spatial audio rendering for such environments is impossible using brute force rendering of all sound sources. Our solution is based on 2 approaches similar in spirit to the occlusion culling and level of detail widely used in computer graphics: perceptual culling and spatial clustering. Both culling and clustering are driven by an interactive estimate of the perceptual importance of each sound source, in our case, binaural loudness. To illustrate the components of our approach, we will use the following test scene containing a train, truck, fire, and a moving helicopter, resulting in the 54 sources shown in magenta. Our culling algorithm dynamically estimates masking occurring between all sound sources in the scene and removes inaudible sources. In the top view, we represent audible sources as yellow ray paths to the listener, while red paths correspond to the culled sources. We next illustrate our clustering algorithm. Based on a spatial error criterion and the perceptual importance of each source, we dynamically fit a budget number of clusters at each frame of our simulation. A premix signal of all sound sources in the clusters can be efficiently generated in software. Costly spatial processing is performed for each cluster only using the location of its representative. Our approach can deal with a variety of environments, such as this train station environment containing 195 sources.
Hurry up, we've got to catch the train.
Poznają.
It can be used for automatic management of 3D hardware voices in video games or simulators. Finally, it allows us to oralize complex room acoustic solutions using off-the-shelf consumer audio hardware.
It could be much more interesting. Actually, I'm making a digital to analog converter. I've been working on the hardware. Oh, that's not so interesting. It could be much more
We ran a pilot validation study on 20 subjects to evaluate both quality degradation and auditory localization impairment resulting from our algorithms. Except for very low cluster budgets, quality degradation was found near unnoticeable, and the system did not significantly impact their auditory localization abilities. In particular, our results did not exhibit a strong dependency on the number of clusters.
The street dataset is a general urban scene with lots of irregular geometry in the form of a tree and vehicles. The aquarium dataset has multiple depth levels, which make it a challenging scene.